Welcome to our second Echem office hours live stream Q&A. I'll let my colleague Alex here kind of take it from here. I just thought I'd say a word or two. Someone type in the chat that you can hear these words that are coming out of my mouth. That would be very helpful, just to make sure everything's connected right. And we'll let Alex kind of
give us a little bit of feedback. Just like what Neil said, just welcome everyone. Let us know if you can hear us. Welcome to the live stream. We are your hosts. I'm Alex Paroff, colleague Dr. Neil Spinner, and the goal here is to try to answer as many questions as possible about electrochemistry. Any and all questions, we get a lot of them through webinars, YouTube videos, phone calls, direct emails, and so we figured this would be a very good platform to try to answer some of those questions. Now, a few things just to note. While the live stream, the waiting video was going on, you could post any questions that you have in the chat. Just post whatever electrochemistry questions you have, and Neil and I will just go through them just one by one. We will put a little bit of priority to YouTube members first, but ask your question. We are happy to answer them. And for those of you who are watching this after the live stream has ended, I plan on adding some timestamps to the video description so that you can find out when, which questions were answered at what time, just in case you missed it. Additionally, we are using Zoom as the broadcasting platform, and we've noticed that there's about a 20-second delay between when we see something on YouTube or when a chat thing comes in and then when we say it live. So just keep that in mind if there's a bit of a delay between the responses. So again, just a shout out. I'm just kind of going through the list of things to say, but we want to give a shout out to all of the YouTube members who are joining us. And I also want to state that for this Q&A session, to ask us anything, there are no stupid questions. Electrochemistry is very complicated, and we're just here to help you as much as we possibly can. So this is a safe venue to ask any questions at all. We're aiming for this to be maybe about an hour, maybe 2 hours, or a little less. If it goes a bit longer, that's okay. We want feedback on whether you like this, if this is a good length, and we're aiming in the future, hopefully every Friday or something like that, we'll try to do some of these types of live streams, of course, as our schedule permits. And we're going to apologize in advance in case we mispronounce people's names.
in case, you mean when
we mispronounce.
Yeah, this is an absolute certainty.
Yes. Yeah,
it's not intentional though.
Yeah. So with that said, just looking here, it's like we have a question from Penn we can take a look at. Penn, if you can hear us, please let us know and type in the chat. He's asked, can you explain the working electrode interface and how does it fit into the Randles circuit? What do you think about this one? Neil, do you want to?
I would love to. Let me get I'll pull up some slides from one of my webinars because I think it'll help show this graphically in a little bit better way than I could just explain. Let me share. See, make sure I get the right PowerPoint presentation here.
It's a very good question, because the working electrode interface is typically pretty complicated. It can be very complicated.
Yeah.
So we think that some of these pictures and illustrations will be helpful, and then how those things on the working electrode relate to the Randles circuit, and then perhaps even he's also asking how does it fit into the Randles circuit. So I don't know if he's also Penn, if you want to if you're doing like EIS circuit fitting, if you're talking about that kind of fit, or just what element.
I would guess it's EIS circuit fitting just based on dimension of Randles element, because that's typically, so just for those who are not familiar with it, the Randles element typically involves, this isn't really exactly the case, but I'll just draw the most basic example of it. So we have The Randles element usually involves, is just a blank slide for me to write on, by the way. That's all that this is. So this is typically our R0, sometimes called our ohmic IR drop, our RS, our series resistor. So this is your uncompensated resistance series resistor. Those are just names of the same thing. And then this would be our, you typically double layer capacitance, or non-Faradaic process, non-Faradaic capacitance. I'm just sort of giving all of the kinds of synonyms for what this represents. And it's a capacitor, or sometimes a constant phase element, which is either represented with Q or CPE. Again, these are all sort of synonyms for the same thing. So either a capacitor or a constant phase element. And then you have your charge transfer resistance down here. And so this is typically used, this whole thing is the Randles element. Okay, so sometimes it's also just, the Randles element is just used to describe this part. And the series resistor. So there's some variation here, but typically this is what we're talking about with the Randles element. You say you're new to electrochemistry, currently doing DC measurements. Is that modeled differently? Yeah, generally speaking. And the reason being that the application of circuit models is pretty much exclusively done through impedance spectroscopy. We are simulating the process. You can let me clarify. These processes are occurring on your electrode at all times, right? If you have some Faradaic process, okay, like an oxidation or a reduction reaction of interest, oxygen reduction, hydrogen evolution, these are all Faradaic processes that are occurring on your electrode surface. You also have non-Faradaic processes like interfacial capacitance at this double layer capacitance right here. Okay, so you have all these processes occurring at the same time on your electrode surface. Whether you're doing AC or DC electrochemistry, the difference between AC and DC electrochemistry is that with AC electrochemistry, like impedance, you can deconvolute these processes as a function of frequency. So you can look at things that are happening at the same time at different time scales. In other words, speed. So some of these things happen faster than other things. Charge transfer resistance happens very fast. Double layer capacitance is a little bit slower. Diffusion is even slower than that. So impedance is allowing, so they're happening and in some sense modeled the same, but the modeling in terms of using a Randles element is more exclusive to impedance spectroscopy. So there, here you see it again. And really what the whole, to your first question, explaining how does it fit the working electrode, this is kind of a small way to kind of illustrate that. If you look at this, just, little cartoon down here, if this green part here is, if this is your working electrode, right, and this is your electrolyte, the blue, right, this is the interface right here. This is the interface between your working electrode. So what's happening is that these are in parallel because the current is basically occurring at the interface. And it can happen. I mean, I'm just drawing over my own arrows here, but right, the current is going simultaneously, depending on the frequency of impedance, essentially to affect this capacitive process or this charge transfer process. Okay. And so that's why it's drawn this way. And I like to, in my webinars and for example, in these illustrations, I like to kind of show it this way, superimposed on that interface, because that's where it's all happening, right? Electrochemistry is it's an interface surface science. So, this resistor isn't just a resistor. It's basically describing that resistance that's occurring right at that interface. And this capacitor is not just a capacitor. It's the capacitance that's occurring at the interface between the electrode and the electrolyte. So that's a very basic and kind of quick run through of those phenomena, I guess I would say. There's obviously quite a bit more that can be said about it. And I have done, not to again shamelessly sort of plug our stuff and my company, I suppose, but what you're seeing here is a slide from my second of five in a 5-part webinar series that I've given a few times, and it's on our YouTube channel. You have to become a member, a tier 2 member, and you can actually watch the replays of all of my webinar series if you'd like. So I invite you to do that if you want to kind of get a little bit more, each of the webinars is like an hour or so with, 20 or 30 minutes for questions. That when I did it that day, I'm going to give that webinar probably, once or twice a year moving forward. I always try to refresh it because people seem to enjoy the content, but you can always watch it anytime on our YouTube channel on the members section. For now, though, we're gonna move on to another question.
Well, there's one other thing I would just say, just to like Penn's second question is about, he's new to electrochemistry. And it's like, it's like he's doing these DC measurements and he wants to know, like, is that modeled differently? And I think it's important just to drive home that.
Yeah, do you want to take the sharing here? If you had...
Well, I was just going to say that.
I'll stop sharing in case you want to do it.
Oh, yeah, sure. So. But basically, what Neil has been describing has been like what we describe as an AC view of electrochemistry, but it is the same model. And I guess I can, it's like, as Neil said, like the same thing is happening. It's just like in DC, all these things are happening. So the model of the Randles circuit it's that same model, whether it's DC or AC. And one way you can think about it from a DC perspective, because I do want to get to Ankit's question. Once I learn how to share the screen,
do I have to enable you?
No, I literally was just like clicking on Zoom.
That's okay.
To get this thing
just to embarrass myself and make you feel better about yourself. We did an earlier version of this live stream, and I talked for about 10 minutes showing plots in our software before I realized I wasn't sharing the software. So.
All right, so people should be able to see this.
Very good at this.
But Penn, you may be observing something where you're doing a DC voltammetry experiment, where you're getting these cyclic voltammograms. Maybe they look a little bit like this, and this will go a little bit more into Ankit's question. And then, as Neil said, you have this solution resistance, and then you have double layer capacitance, and then you have some charge transfer resistance, right? And your working electrode is here, and then your other electrodes are over here. But you can think about it like this is the DC technique. This is what you're doing. And so at this point, you can think about like, well, the resistance here, what we call RCT, or the resistance of charge transfer, that's really, really high. So at this point, RCT is really high. But at this point, where we have a lot of current, because this is current, this is voltage. At this point, RCT is low. We're getting current to flow. So this is, in a way, the DC view of this type of model. But this model is used a lot for AC, but with DC, this is how people can think about it. And then solution resistance tends to manifest itself as kind of the position. This kind of position is offset in a way when this R omega or solution resistance is changing. So that's just one thing I wanted to bring it back to. Like, is it the same model? It is the same model, kind of thing.
Yeah, the values are just different depending on what potential you're at and stuff like that.
Yeah. So if I just go back to Ankit's question, he's asking why are we always getting irreversible or quasi-reversible CV graphs instead of nice reversible ones? So there's several things that could be happening. Again, I'm going to just draw my voltage. I don't know much about your system. Please type in the chat more information, details about the system. But you're talking about a case where you're getting something that looks like this, and then instead of the reverse wave, maybe it's something like that. Maybe that's what you're getting. So where is this? Where is your nice reversible wave? There's several things that could be happening. One is just quite simply, this electrochemical process is it's irreversible. I actually dealt with something like this in graduate school where hydrogen or whatever irreversibly absorbed onto a metal, and then it just didn't come off. Just didn't come off. So that's one thing that could happen. Another thing that could happen is that you have a chemical step after you do your electron transfer. So this is a case where, and I think annotate has something like, if I have A, let's say this is let's just say it's a reduction. A plus an electron goes to B, and ideally this is reversible, right? But I also have another. Oops, that is my email address. That's just no, that's my signature. Sorry. I was emailing someone before this. But if I go back and I can just do this. Okay. Maybe B reacts with some other molecule in solution. Let's just call it C. Maybe this is an irreversible reaction. So B plus C, maybe that's the solvent, becomes D. So now, if the reaction here, if this is very fast, so let's just say this is very fast, then you're not going to get the reversible wave because you need the B to oxidize back or to do the reversible step to go back to A and the electron. So if this is very fast, that's one reason why you might not see this peak. Another reason, and one way you can, one thing you can do to experimentally verify that is change C. Like maybe C is an acid, maybe C is a base, maybe C is some solvent, and if you change the solvent, it's now reversible. Another thing you can do to tease this out is scan faster. So do faster scan rates so that there's not as much time for B plus C to go to D. If you do this process fast enough, maybe B doesn't have as much time, and you'll start to see these you're like, oh, there's a little bit at one scan rate, and when you go faster, it's a little bit more. When you go faster, it's a little bit more, stuff like that. So those are, I guess, just very quickly, a couple things that you could do, and reasons why you see these irreversible types of CV graphs. Okay. Do you have any comments, Neil, or
no?
thoughts?
As I'm ignoring everything.
Okay, all right. No, it's all good.
No, so what I'm doing,
that answers the question.
Yeah,
catalysts.
So you're gonna cover for me for a second here. The next question here, is I see from Pranesh Nandan has asked a question about a Nyquist plot. I'm gonna I'm prepared. I'm trying to prepare a quick thing because I'm gonna try to answer this question. I have a little bit of data that I can try to use to like kind of answer your question. Give me like one moment. So you Alex,
that's all fine.
Continue for a second for me, cover for me here.
Hello, my lady. Yeah, I can just like be entertaining.
Yeah. Do a dance or something.
Hello, my lady. Hello, my darling. Hello. Yeah. Just like that on the frog.
Yeah.
Okay, so Ankit said that metal catalysts. Ankit, what kind of metal catalyst, what kind of reaction? Actually, that will be one of the biggest type of questions, is what kind of catalyst, and are you getting catalysis? Because when you do get catalysis, actually, this is a very good point. I'm going to go back to sharing my screen. So if we have a catalyst, what can happen is, let me go back to draw. So let's go back to the CV plot. If it depends on what the catalyst is. If it's a homogeneous electrocatalyst, so homogeneous, I don't know if I'm spelling that right. If it's a homogeneous electrocatalyst, then what happens is this is the kind of situation where you may have seen these types of pictures or plots in, I can actually erase this for one moment, but you maybe have seen these kinds of pictures or plots where you have the electrode surface and then your homogeneous catalyst. Usually they use P's and Q's most of the time.
Mind your P's and Q's.
Mind your P's and Q's. So P is your catalyst. It gains an electron from the electrode, and then it becomes Q. And then Q reacts with the thing that you're catalyzing. Let's just call that A. And then that forms B. Okay. If you have this type of situation, if there's a lot, like in order to have a reversible CV or redox species, Q's got to go back to P and then put the electron back into the electrode. It needs to like oxidize. But if Q gets consumed, right? If Q gets consumed to form, you know, to maybe form, not get consumed because it's the catalyst, but it doesn't actually go back to becoming P. What you end up getting are these voltammograms where you have a.
Sorry, I've had the face on me the whole time.
Oh yeah, that's okay.
It's
all good.
I was working it out. I got my data set. Anyway, continue. Please continue.
You know, when you have a regular voltammogram, maybe you get something like this. But when you have catalysis, you end up getting this huge increase in current. And then it comes back down like this. So that's the, and if you have weird types of currents, stuff that can happen, the shapes are always a little strange, but they always tend to look a little irreversible in some way. You almost rarely see anything on the oxidation or on the return wave when you're doing some kind of catalysis.
Also, probably good to mention simulation again, right? I mean,
oh yeah,
right, like simulation, like CV simulation software. Usually, you can work out different mechanisms, like, you know, usually those kinds of things. So we've got that coming as well. Sometime that's not Alex or I's area of R&D at the company at the, you know, but anyway, we have been working on a simulation platform basically to do this sort of thing, right? To simulate you know, different electrochemical chemical processes and everything like that. So everything that Alex is describing is you know, the kind of thing you can also look at with a simulation software. So.
Another thing, if you still need some time,
I'm good now.
No, you're good now.
Please continue if you have information to give.
The very last thing, the only other thing that could happen is some cyclic voltammograms that have very slow kinetics, and that's a terrible drawing. Some CVs actually, if they have slow kinetics, you won't actually see the return wave until much later. Yeah. So, and that has to do with, that's just the kinetics of the molecule itself. Like sometimes it just has a lot of the reorientation energy barrier is heavily favored in one direction. This is where like alpha kind of comes in. It's very much favored in one direction, either the oxidation or the reduction, but it's not very favorable going the other way.
Yeah, asymmetrical reaction.
It's an asymmetrical reaction. So that's another reason why you only get one, and then by the time you're actually at the potential where you know, you're supposed to, you know, revert it back to the original species, some of it's just diffused away from the electrode surface. So that's another thing. But I hope that was helpful, and I will stop sharing. And
sharing is caring.
Sharing is indeed caring.
So, okay. Yeah. Thank you for continuing there for me, Alex. Cause I saw Pranesh Nandan, you asked a question. You have a Nyquist plot that has a linear trend with a slope of around 0 degrees at high frequency, followed by a semicircular trend. Can this linear portion be attributed to an oxide or a barrier on the electrode? So just to be clear, I'm guessing, let me share our software here with you. I'll select the right application, I promise. Let's see. Okay. So for example, you might have something like this, right? This is a semicircle. It has a little diffusional tail, but essentially something like, instead of that, I made a sort of modified version of this, right? So it's like this, but there's this kind of odd looking lagging. This is just doctored data. So this is like a perfectly sharp angle. I doubt very much that, you know, your data goes perfectly like this, like mine is, right? This is a bit, yours is probably like, maybe there's a bit of a lag, and then it, you know, something like that. You might have this high frequency kind of behavior, like something like that. I'm just sort of guessing here without any further context. So the first thing that I would say about this is that you want to verify whether this is even real data or not. The kinds of things that happen at high frequency, especially stuff like these lagging kinds of, you know, features, or sometimes you get stuff that looks even more suspicious, like you might have a little curl, you might have a high frequency tail that would finish in, you know, negative Z real territory. You might have some kind of features like this. All different potentiostats, different kinds of situations give weird stuff like this, and these are generally, like in the literature, you'll see this word artifacts, and it's not talking about something that was discovered in an ancient tomb. It's a feature of the cabling and the reference electrode and all kinds of weird things that are contributing to this bizarre behavior. But essentially, the thing to take away from it is that it's not really real, or it's not related to your system. So now your assumption of an oxide layer is not necessarily incorrect, but the first thing you want to do is something called Kramer's Kronig, if your software has it. And so in this case, I'm guessing it's going to be totally nonsense, because I've just intentionally doctored the data to add this sort of feature to illustrate something that I'm guessing that you're seeing. So in my case, you see that this really does not match whatsoever. So if I were to have data that looked something like this, and then I did Kramer's Kronig, and I saw this kind of lack of fit at, especially at the high frequency. Now, as I get to mid to low frequencies, starts to look great. But at the high frequency, I would say, okay, well, this is definitely something wrong here. So I wouldn't think about this so much as an oxide layer. You know, when you're thinking through some sort of a process, the KK fits these points. Okay, so I'll finish this thought, but then I'll move on. As you said that you've done Kramer's Kronig, so that's good that you have that intuition to do that. For those who aren't maybe aware of this, if you were to get data at high frequency or other kinds of, well, really anywhere, but in particular this kind of case, and it doesn't fit your Kramer's Kronig, it's a good indication that it's not valid impedance data. Something is not really worth, it's not worth analyzing. You could cut this part of the data out and analyze the rest of it, or try to retake your data, perhaps starting from a different frequency, something like that. Now, the first thing I'll say to the idea that the Kramer's Kronig does match, as you've said, is it's dangerous, because Kramer's Kronig basically does, it can't give, let me think this through, say this the right way. It can give you a false positive, but it probably can't give you a false negative. So in other words, if it doesn't fit, that's a good indication it's not accurate. But if it does fit, that it can sometimes have a false positive kind of result, because Kramer's Kronig is purely mathematical. So like, for example, it can fit if you have like negative data, negative impedance, but there's really no such thing as negative impedance. So it's like, it'll fit telling you that it's valid impedance, but is it really indicative of something that's really going on your electrode surface? So that can be tricky in that case. Now, to the question about, you know, an oxide barrier, an electrode, possibly. Typically features that are like this, where they lag or they have a, you know, the 0 degree angle to me is strange, because you know, it's hard to consider a really, really low angle like that to be related to like a real verifiable process. Most often, even if you have like some kind of oxide layer, or you have some sort of a porous electrode, you might get like what often looks like a transmission line model, which has more of like a lagging feature. And then it might, I'm going to exaggerate this, for illustration purposes, and then like a semicircle. And so it's like, it's the opposite of like the Warburg, where this, 45-degree feature is at the end. In this case, it's like at the beginning. So typically this kind of feature here is something like that. So when the line at the beginning instead is down here, it's really tricky because there aren't really any circuit elements that easily fit something like that, apart from a constant phase element where your alpha is very, very small. And then you're down to the question of, well, what does that mean? Right. And so it's hard to answer that question. I have seen in some cases, the explanation, for example, of an oxide layer, something like that. But some kind of a barrier or an extra layer, most often the kind of data that I see, for example, let's say you have like some kind of interface, maybe like a film or a substrate, and whether that substrate film is like a layer of actual like deposited film or it's an oxide layer. A lot of times you just get this small semicircle, and then you'll have your sort of normal feature, and you change potential or whatever, you get a different spectrum at a different potential. You might have a higher or lower Faradaic process. You might have a higher or lower Randles element, but this beginning semicircle will always remain the same. That's really an indication, no matter what potential I'm at, that it's an immutable characteristic of that electrode in film or oxide layer that's really not changing. But less often is it this kind of a thing. And really, I'm always very wary of the whole like horizontally moving impedance line. I find literature, it's not very common, and then when it is, I find it to be one of these things that isn't well understood and isn't well, it's mostly speculative as far as what, like, even in the literature, there's no consensus like what's going on. It's like the inductive tail, if you've heard me talk about that before. It's like, what is exactly going on? It's not clear, is the best that I can tell you. So I think it's possible that your explanation could be accurate, but difficult to prove at best would be my proposal for that explanation. Unfortunately, right? I guess I wish it were actually easier to use that as any sort of analytical tool. It's just that feature is really quite problematic. And again, the problem is that there isn't really any circuit model to fit it. It's like, if you can have a circuit model to fit it, you can easily attribute some process to it, right? If it's a resistor, you can say it's some sort of charge transfer process, or it's a, interfacial capacitive something. It's there's all kinds of, each of these circuit models, right, have some process that's sort of relatively conveniently describable. The best that you can do, like I said, is if you have a CPE and alpha is close to 0, it's something like a almost a non-ideal resistor that's exhibiting small amounts of capacitive properties. But that's pretty vague. And what that exactly means is also not clear. So that might be the best that I can kind of offer for that feature there. Unfortunately, I wish I had a better answer, but I'm not sure that I do.
Mm-hmm. It's very good. So I want to, there was a question from Kute about what is the typical CV graph of ionically conductive electrodes. I want a little bit more clear. I mean, is he talking about like an ion selective electrode or ionically conductive liquids? Because those are different types of
like
things.
Ionic liquids is a whole different.
Yeah, that's a whole different thing. So Kate, I wanna answer your question. I just want to get a little bit more specification to address that, but we can go to the next question. and then come back to that. And the next one's from Guru. I'm actually not 100% sure. Neil and I have actually talked about this numerous times, and really we need to speak to someone who's an expert in photophysics and stuff like that, which is to talk about the kinetics of single electron redox processes on metal electrodes versus semiconductors. And how can they be distinguished from, like, the Fermi level is different for them. And I have a very limited understanding of it. I can just kind of just share very, very simply. The electrode surface. So my understanding of certain things is this. Let's say you have a molecule. Let's use like HOMO-LUMO gap type of things. Like, this is the energy of your molecule. So this is like the HOMO highest, or no, it's the highest occupied. So that means I need the, let's go with the LUMO. So the lowest unoccupied level. So let's just call this the LUMO. And then if you have a metal, right? So you have some kind of metal. What I've always been taught is the metal has some kind of band, or actually the metal has some kind of Fermi energy or potential level, right? Some number of electrons. It's conductive throughout. And when you use a potentiostat to apply a potential, you are moving this entire thing. So actually, I don't know if I can do this in here, if I can highlight an entire thing. Let's see. No, I can't do that. I can't select this entire thing, can I? No. So basically this entire block will actually move up. Let's see. I don't know if I can redraw this. Maybe a better thing to do is here. So instead of this, I'm going to use this drawing tool. Draw. It's going to, oh, sorry. I want to clarify this because, hold on. Let me start over from the explanation, because what you end up having is you have some kind of a band and it has a level. And then you have, what you end up doing when you change the potential is you have that same band and you move it, you just move the whole band up. So if this was the level and it was here, you've now just moved the whole thing so that it's still here. But now I'm at a point, because these are electrons and stuff. I've moved this up by changing the potential with my potentiostat. And now electrons can move into the LUMO, the lowest unoccupied orbital of my molecule. So hopefully that makes a little bit of sense. And
the last part of this question is, he's asked, how can we use electrochemistry to distinguish between the two? So
between the Fermi levels.
Well, but just between, semiconductors and metallic conductors.
Yeah.
I guess to that, I would say that, there's this weird that we recently came across this. There was one, it's actually not as common as I kind of thought. I want to see if I can pull up let's see, I had a paper recently that I wasn't sort of looking at. So what your one way to think about your question or sort of answer it is in considering electronic conductivity, for example, because one of the things that is different between the two is that semiconductors are not as conductive, hence they have a larger band gap. It's like there's an energy source, there's an energy that needs to be supplied to make it conductive, whereas a conductive metal does not require such supply of energy to cause electrons to move, basically. And so obtaining electronic conductivity from electrochemistry is actually not quite as common or obvious a thing, I think. So there's this one publication here that we found, or one of our customers had found. I'll kind of show it here, sort of a quick plug of this group here from, it looks like the University of Washington. So they were looking at ionic and electronic conductivity. So ionic conductivity is more commonly done with electrochemistry. You know, you can do like 4-point probe tests and membrane tests to get a measure of ionic conductivity. This is a pretty common thing. You get a measure of the resistance and you can equate it to the conductivity of a membrane or something like that. But electronic conductivity is not quite as common. What I would say is that one of the things that's kind of unique about electrochemistry is that you can do, they also have an energy gap, which is forbidden due to the lack of density of states. I'm not sure what you mean by forbidden. That's a little bizarre. I guess the point that I'm going to make here is that electrochemistry is somewhat unique in the sense that I did like studies on nickel oxide when I was in graduate school, and nickel oxide is a semiconductor, but it doesn't really matter because it's like the potentiostat does the work. Like when you're doing electrochemistry, that's kind of what you're doing. Like the potentiostat, like you need to get to a certain, you know, like for example, if you're doing a reaction on platinum or something, right, or silver, copper, these are all conductors. It might have a certain overpotential required. There might be a higher overpotential required to do it on a semiconductor, like a metal oxide, like nickel oxide or whatever, molybdenum oxide, something like that. Okay. So it might have a higher overpotential because it's not kinetically favored. You have to overcome a band gap, all those kinds of things. But all that is done, like that's potential. The potentiostat is doing it for you. So it's like, it's like there isn't a distinguish other than just the like potential overpotential at which something is occurring, you know, difference between the two materials. That's one way to kind of look at that. But like, in some sense, it's like electrochemistry isn't really used to distinguish between the two because electrochemistry is used to gain data from either. I don't know if that makes sense, but that's kind of the way I think about it. It's like semiconductors are tougher, but you can get information using electrochemistry from them anyway, even though they have less conductivity, because the potentiostat, the instrument you're using, actually overcomes that deficiency.
Yeah, it's strange because a lot of the things he's talking about with like density of states and transitions that are forbidden, these are all like photophysics related like concepts, and it has to do with excited state. So one thing to be very clear about is most of the time these semiconductors, you know, you're shining light on them and then you're exciting an electron to an excited state. In electrochemistry, you're changing in some ways, not the band gap, but the position of the band gap relative to everything around it. And I personally don't know enough about its manipulation to say, because you can actually get electrons to come from the solution to go into the semiconductor. You can actually, it's not just create an excited state, it's adding electrons or removing electrons physically. Like that's what electrochemistry does to these semiconductors in many ways. So I don't know if so I don't personally know enough about using electrochemistry to distinguish between a pure metal conductor and a semiconductor, unless you use light and photoelectrochemistry.
Because that's a good point, because the light spectroscopy or spectroscopic, different, you know, versions of spectroscopic techniques are doing just that, to measure those wavelengths or energy required to excite electrons into a state, you know, over those band gaps. You know, I think that's a good point, because if you're trying to distinguish between the two or get some sort of measurement to between the two, that's exactly right. You're looking at spectroscopic techniques. Electrochemistry is not distinguishing between the two, but it's great because, as I said, you don't need to care or something like that, right? The potentiostats doing it. Electrons are filled till the valence band.
And levels above the valence band are not accessed, thus this limits the potential. Maybe because if your semiconductor is your working electrode, you can change the potential. That's correct. Yes, light can reach the valence band. The levels above the valence band. But like that's the thing, because electrochemistry, because you can see, I don't know if it'll show up, but it's like, okay, you have this one band and then you have another band, valence band, and then light has to traverse it, so you get one to go to the other. Those both have, like, the potentiostat allows both of those to move up and down, and then things next to it will react accordingly, sort of say. But that's a good question, and something that I think we may want to investigate some more.
I've had this discussion a lot too over the last, several months or even a year or something like that. And it does tend to be one of these ones that's like, it's a bit abstract to the study of electrochemistry in particular.
Yeah.
Right. And I always also find myself like trying to figure out how it fits and what the explanations are. It's a little tricky.
There's a guy named like Jim Cahoon at UNC. We have to pay that guy a visit at some point and just like pick his brain. I think Kute here gave us some more
hydrogel coated metal electrodes. What I would say in short is that if you're worrying that your material is really thick and not a liquid, you can still get electrochemistry. So how the CV looks, that's not really a question that we can answer. Like how any CV looks is dependent on a million different things. Right. It's what redox processes are going on, and what your system is, what your electrode is, and everything. So the fact that you have a hydrogel that where ions can absorb in and out and everything like that. I mean, the short answer is I have no idea. But the other short answer is that I would not expect CV to be severely inhibited. You might just have some more sluggish diffusion. In a more gel or less liquid, solution, perhaps higher impedance, things like that. But I would not expect an inability to get CV. But as far as what it looks like, hook up stuff and see. I don't know.
I think you're right. I think the diffusion would change the most, but your CV will maybe if you simulated a CV with like a very slow diffusion coefficient, it would I think it would just be elongated a little bit. But that's a guess.
I'd have to look at that actually. I'm better with impedance about how it doesn't look for diffusion. How the diffusion affects it would affect the peak, it would affect the peak, because if you think about a CV peak is the impact of Butler-Volmer kinetics. Where's my camera? Butler-Volmer kinetics and then diffusion. And Cottrell, that's the Cottrell equation. And so basically if your diffusion is more sluggish, I guess shouldn't the current drop more aggressively because it's like there's worse diffusion, so you get less current, or be drawn out further. It's one of the two, but it would probably affect the shape of your peaks. The latter half of the peak is related to the diffusion of species to the surface. So something like that. It would affect the.
It might affect the current more.
Well, that's what I mean. I'm sorry. The current, like your
shape
peak
will look the same, but the current values will.
Maybe the current values will change, but I would expect the shape to be slightly different because anyway. I'm not 100% sure, but it might affect the peak shape in some fashion. But that's actually we should probably at some point simulation software again. You can kind of tinker with diffusion coefficient and see how it affects exactly. But it'll probably affect the way the peaks are constructed, I guess, or manifest.
Jill had a question, which was, can you explain RCT, the charge transfer resistance, in simple terms? It's like he asked this question a while ago, and but it takes a while to answer these. But my very, I guess my simple answer would be, you can think of it as it's a resistor, but it's not, but it's a varying resistor where the resistance changes as the potential changes. So RCT is very large when you're at a potential that's not close to the redox potential of your molecule. But once your potential is near the redox potential of your molecule, now the resistance gets lower, and it's easier for an electron to physically cross the electrode interface from the electrode through the double layer to the molecule, and vice versa. And the charge transfer resistance is just the resistance value for that process.
Yeah.
I think that's,
I would sort of,
hopefully that's helpful.
If you're thinking about it in terms of, you said explain the RCT and the charge transfer. So, I mean, if you're thinking, what's the charge transfer? I mean, that's really just, that's the movement of an electron from one thing to another. So, I mean, the most basic kind of A plus E goes to B, explain the charge transfer. That's where the A moves from one thing to another. So, right, whether it's, in this case, it's a reduction, A is getting reduced going to B. This is like, like iron 3 plus an electron goes to iron 2 plus, or whatever. It could be anything, right? But I'm just any random example. It's like, what is the charge transfer? It's just the addition of an electron to the species to change its oxidation state, or removal of an electron. So that's the, most general basic kind of definition of what's the charge transfer. But what the resistance is, as Alex said, is that it changes depending on what potential you're at. But if you have this, let's say you have iron, is iron between 3 and 2 or 2 and 1? Is
3 and 2.
3 and 2. I thought so.
2,
Okay.
generally speaking.
So I'm not crazy. All right, good. Maybe it's copper. Copper's more like 2 and 1. Yeah. I'm just trying to come up with some random example on the fly here. And I might be making something that doesn't make any sense. So pardon me if this isn't accurate, but it's just for illustration here. So for example, if you have this as something that can happen, well, there's some like standard energy associated with this. There's also like a Gibbs free energy associated with this. These are related based on the Nernst equation. But effectively, there's an energy required, like this will happen, one way or the other, depending on which species you have. But when we talk about the RCT, that's like, well, it's like this could happen in either direction, but is it going to happen? Right? Well, there's some energy to overcome one way or the other. If you have Fe3 plus in solution, is it just going to necessarily become Fe2 plus? Or if you have Fe2 plus in solution, is it just going to necessarily turn back to Fe3 plus? That's where I'm trying to be very, very vague here, but that's where the RCT comes from. Or in some ways, it's like there's that's why these things are drawn in terms of circuits, because it's just the most simple thing is that you have a resistor. This is some value, and it's going to oppose the passage of current. Electrons want to flow, but they get stuck. They can't, because this resistance is really high. But if this resistance is really low, electrons can move very easily and make it from one side to the other. Just depends on what the value is. And so that's what changing the potential does for you. By changing the potential, you can raise or lower this charge transfer resistance to do this process, whichever direction you're going. And so, when you do impedance, for example, you're measuring what that is very directly, depending on what potential your set point is at, and you're measuring the value of this resistor, however many ohms it is. But the ohms is basically comes into play for Ohm's law, right? So V equals IR. So whatever this resistance is, it's telling you if I want to get current to flow, I need a certain potential, or vice versa. If I want to get a certain potential, I need a certain amount of current based on whatever resistance it is. Okay. So I hope that's helpful. That's about as simple as you can kind of get on that topic there.
Yeah, let us know if there's something that was a little complicated. There are a couple questions.
George had some questions about New York.
Yeah, I asked them for a little bit more clarification because there's New York City, there's New York State.
Yeah.
Also, general use or external users. I don't know about things like that.
Yeah, I don't know. I mean, there's a lot of universities in New York that have our products. I don't know if they're like accommodating for, people coming in to do. I mean, certainly like collaborative efforts happen, but I don't know. I have no idea how. Like, if you want to go to like SUNY Binghamton or and do some work, you have to know somebody. Or I mean, you could email a professor, and say, hey, do you mind if I squat in your lab for a little while? Like that may certainly be something they can do, but I don't. We don't have a knowledge of that as a company or a policy per se, right? That's sort of on a case by case basis. Yeah, we certainly have people using our stuff, and if you're looking to do glucose screening stuff, you just need a very compact, small potentiostat and probably some screen printed electrodes.
That's right.
Or just a simple 3 electrode system with glassy carbon, platinum, silver chloride, something like that. Like a very simple, basic set of equipment. One simple potentiostat with a low voltage and current capability. You don't need a lot, right? You don't need this massive system. Small 10 to 20 milliliters of volume, something like that is all you really need to do some of those kinds of screenings.
Okay, wait. All right, he's gonna be at Cornell. Talk to Tito Hector Brunia. He'll hook you up.
Hector Brunia is like a superstar.
Yeah.
He's still at Cornell. He is still.
He's still at Cornell.
Yeah. He's a really great guy. And he's got a lot of equipment of varying degrees. And probably a decent amount of labs. I've never been to his labs, but I bet he's got a million potentiostats and everything.
And a bunch of rotators.
Yeah.
He's got a lot of stuff.
I mean, I don't know. We're not volunteering him by any stretch of the imagination. We're not.
I'm volunteering.
Okay, well, Alex is volunteering. I'm not, but he's a very, very nice, very nice guy, and he's absolutely brilliant. So perhaps he'll be amenable to something like that.
Yeah. There is there's another George or Jorge from Brazil, and he is asking about, I'm assuming it's a he, that he wants to know the choice of scan rate for linear voltammetry for oxide growth analysis. And as a follow-up, he has a linear relationship between the current density and the square root of the scan rate. How can I select the linearity interval? So usually when you're using like the Randles-Sevcich equation and you're looking at peak current, and then you get, so if I go here to, let's see. So if I go, all right, annotate. So you've probably seen things where like, okay, you do a CV experiment, and then you do it at like a faster scan rate. I'm very bad at drawing, but basically these peaks increase when you get the square root. So you're getting square root of scan rate, and then you have current density.
Yeah, or the peak current or something.
Yeah, peak. It is peak.
It's technically the peak current density, which I assume that's what Jorge's referring to.
Yeah, so if you have peak current density, and I'm just gonna move it here, it's the y-axis. You will get something that should look like this, generally speaking.
Right.
You should get a straight line. It's a linear relationship, and this means that you have a homogeneous diffused electroactive species in solution, which makes it a little hard to understand or think about oxide growth, because I don't think oxide growth has this type of linear relationship. Imagine you have an electrode, and that as you scan the potential, this film like increases, but I don't see the current necessarily increasing linearly with the scan rate per se. But I mean, I don't know. I mean, maybe that has to do with, you may have oxide growth because you have a species that's, diffused in solution, that's continuously, it's continuously oxidizing on the surface, you know, depositing. And so maybe that's why you're getting a linear relationship. George, correct me if I'm wrong in my analysis, because I'm just, you know, Neil and I are guessing most of the time about the systems that everyone's talking about.
Yeah.
So any additional confirmation is, I'm just going to stop sharing so I can look at if there's any follow-up, but any additional confirmation about the system is always appreciated. Let's see. So his name is Hector Abreu.
Oh, sorry, I'm getting.
Oh, you're typing it.
Yeah, I got his
Yeah. Oh, yeah.
his link, his faculty page there. Sorry, we were duplicating.
There's also plenty of other electrochemists.
Yeah.
Jin Sentovich, Song Lin is a organic electrosynthesis person. All these people. There's a bunch of people at Cornell who do electrochemistry, but Hector is the most well known to my knowledge. But yeah, I don't. Let's see. Growth oxide. Yeah, it's so the question about growth oxide analysis is like, what kind of analysis are you interested in? Like if you're interested in how much oxide, the thickness, you can look at the current over time, get a number of coulombs of charge, and then relate that back to the molecule itself to figure out how much has been depositing on your electrode.
Yeah, and it's just something like chronoamperometry as a possibility to monitor current.
Let's see,
current, because like it's an easier, like you can integrate under a current time curve, or to get something like that. But if you just do chronoamperometry, for example, you can get an easier sort of calculation of how much current's passing over time.
Yeah. Let's see, George is saying an ohmic ratio up to the peak condition, oxide fully formed on surface. Yeah, so ohmic ratio. So I guess as he's increasing the oxide film, I'm assuming the resistance is going up. That's, I think, one thing to keep in mind about increasing the scan rate in general is that for non-Faradaic processes like double layer charging, it has the current associated with double layer charging has a linear relationship with the scan rate, as opposed to a square root dependence on the scan rate. So just keep that in mind as you change the scan rate of your species, generally speaking. So I hope that's helpful. If you continue to ask us more questions, more specificity, things like that. So
I see another question from Guru is about two reactions taking place simultaneously. How will the kinetic depends? Can you determine the rates of individual reactions? So
if I have two,
when you have two reactions happening at the same time, that's when impedance comes into play. And often you have a lot of things happening at the same time. Even in a CV, like the kind of curves that Alex was just drawing, you have a lot of things happening at the same time. You have even in just a single Randles element, you have a capacitance, you have a charge transfer occurring. Those are all happening at the same time. That's why I talked about a little bit earlier in this session about impedance. It's one of its primary benefits is that it can deconvolute processes that are occurring at the same time but at different rates. So in the case that you have two reactions occurring at the same time, let's just say that you have two reactions occurring and they are both like Randles element kinds of reactions. So you'll end up with like two semicircles, for example, if you do impedance analysis. So each of these is its own charge transfer process, right? So if you're doing impedance, many times what you can do is just get two semicircles, and you're actually doing, forget about all this for a moment. I'm just sort of focusing on the two processes. But if you have two semicircles that are distinct and separated, I mean, it may not exactly curve down here. You might end up with something like where there's an inflection between the two semicircles, but there's two distinct semicircles. That means that you can actually deconvolute those two processes. And then that's when you can do some kinds of analyses. Like, so exactly getting the kinetic information, you can get information about timing, for example. So if you have C1, R1 here, for the first process, R1, and then this is like R2, and this is C2. So for example, the time constant, which is about the rate of the reaction, the speed, essentially, it's more like, it was like 60-something% of the reaction to take place, but it's basically, that's sort of pseudo-kinetic information. It's like a speed. It's not I know it's not a kinetic constant, but take it for what it's worth right here. And then the time constant for the second one would be R2 times C2. So you can get information from impedance, for example, about like the rates of of each of these Randles elements, these time constants. Okay, so that'll give you sort of the speed of the two processes that are occurring. So that's one way you can kind of deconvolute two processes are happening at the same time, impedance. The tricky thing is, of course, when you get sort of one semicircle, but two processes are happening, that's when it's hard. It can't always deconvolute, because like if you were to put one semicircle here and one semicircle here, well, but you're not seeing two, you're only seeing one, how much is one process, how much is the other? You can't really decouple those, right? So there's a method called distribution of relaxation times that I'm not really familiar with. Excuse me, that I'm not personally very familiar with, and I haven't done myself. But there is as far as I'm aware, this technique can be used to try to deconvolute processes that happen at about the same rate when it's really tricky, because otherwise there's almost no way to really probe multiple processes that occur at the same time and at the same speed, right? Because it's like, you might so for example, you might have processes that happen at the same speed, but they happen at different potentials. So it's like, okay, well, great. Well, I can just change the potential I'm at. Fine. Or you might have them happen at the same potential, but they're different speeds. And so you'll get these two semicircles. So that'll help. But it's like, if they're happening at the same potential and at the same speed, same kinetics, same everything, but there's two different processes happening, like, best of luck to you. It's really, it's just fundamentally difficult to like get a lot of individual information about those. The distribution of relaxation times, as I said, DRT, I know of it and I haven't done it, so I can't speak more to it. I just know that it's a process. So you might sort of find some papers or find some publications that detail that method, and that might take you to a direction that would help you. I can't speak more to it though, personally. I don't have a lot of experience with that method.
Okay, I think I think that's I think that was great.
I think hopefully we got to everything.
I think we got to just about everybody.
Asked. If we didn't, our apologies.
We'll have more of these if you guys if you want them. Leave a comment or something.
To be honest, I think we've discussed doing this a few different ways, right? We did our first office hours several weeks ago. We kind of mostly just prepared some answers, to kind of go through some questions we had gotten in the past. I'm more of a fan of taking questions like this, when if you're joining us and you have questions live, it is a hard spot. Yeah, exactly. I kind of like the live interaction and we're not, the danger, I guess, I say danger, but like, is that we don't necessarily know the answers. Like we have whatever knowledge base that we have. And, it's a little bit easier in some sense when, I make a webinar, I've had time to really formulate the data that I'm showing and understand it a little better. And, in this case, it's like, hopefully we can give you satisfactory answers. I hope that we've done that. But in any case, in the future, probably next week we'll do one of these again. And we'll try to treat it in a similar way. We'll try to show up once a week and sort of have these ask us anything office hours sort of sessions, like with your professor sitting in the office just waiting for someone to come in and ask a question about something, if there are any. We'll continue to do them if there's enough people and asking questions and having good engagement and everything. And if there's still interest, we'll be happy to keep doing these.
Yeah. And
so I don't know if you had to say anything else there, but
yeah, I mean, after this video is created, if you have further questions, you can write comments and stuff.
Yeah, comment. This will be a video on our YouTube channel, this recording. So
yeah,
make a comment on it. We'll answer it that way too if you need it. Otherwise, if you have more questions over the next 7 days, maybe we'll see you here next week.
Yeah, maybe we'll see you here next week.
So we'll do our best to answer with whatever knowledge or resources we have. So
all right, very good. Take care, everyone.
Yeah, take care, everybody. Thank you so much for joining us.